Hope you had a nice lunch. So I'm going to go back in the field for the next day and talk to you about the 2008 eruption of Titan. So first, coming back also to our field work, I was thinking about this, one of the questions that Marcus asked us, and I'm trying to give you some answer about what's the physical volcanology perspective when we go in the field. So especially when we talk about Tephra, Tephra are important because they are basically the primary product of an explosive eruption, and they retain critical information about volcanic processes. In particular, for what concerns the particle morphology and texture that are related to the processes that occur immediately before the fragmentation process, and the deposit characteristics that are related to more to the eruption dynamics in terms of dispersal, sedimentation process, and so on. And all this information are useful in terms of characterized volcanic history, other than risk assessment or forecasting of future events. These information are particularly important because, as in the case of Titan and of rhyolitic eruption in general, they are not occurring very often. In fact, Titan is basically the first rhyolitic eruption after the eruption of Nova Rupta in 1912. So basically, whenever these kind of processes occur, there is quite a large interest in the scientific community. For the Titan, so here some basic information about the eruption. One complication is also the fact that this volcano was not thought it was going to erupt. There were not documented historic eruption before the 2008 event. So basically, there are not even geophysical data available, save for some data collected by a regional geophone network in the area of Chile. So I went there with a group with Costanza, Chuck Connor, Alain Volentic, and also David Pyle and Sebastian Watt. At the time of the eruption, here to give you just an example of what was the activity, basically it was related to a dome extrusion activity with some small plume production, minor pyroclastic density currents, and associated columns. When we went there, this was some picture of the village, which is about 10 kilometers south of the volcano. It was basically a ghost town because it was evacuated during the Plinian phase and was also hit by a minor lahar that creates some major damages. The area was basically, the economy of the area was basically based on agriculture and tourism, so this eruption had a heavy impact. These are like some example of what can happen in a couple of days of ash sedimentation to the plants and trees in the nearby forest. So now we talk about a little bit of the stratigraphy. I divided the stratigraphy in two main parts that are completely unrelated to the one to the other. So this is the stratigraphy. South is the crater, so here. And as you can see, it's a very nice sequence of ash layer ranging. Sometimes they go inside the size range of the lapilli. And as you can see, it's fairly complicated, even though the overall this overall section tends to be kind of easy to interpret in the field because it's fairly it has a variation in thickness that you can map very easily in the field. Then we go north and east of the crater, and the stratigraphy is completely different. In particular, we identified this what we call a beta layer, which is the most thick individual Tephra layer in all the stratigraphy that reaches up to about something in between 15 and 20 kilometers at about 5 kilometers far from the vent. That after that became basically my main focus in characterizing the eruption. So here some isopack map in the proximal and medial area. So basically we observed up to about 50 sample points, splitted half and half in southeast and northeast. And these are the main eruptive events that we could map based on our stratigraphic records. If we go and see some satellite image, so we can consider May 3rd and May 5th, and the activity is show a dispersion towards southeast and east. And basically, if we split the stratigraphic sequence in this area, this is what came out. So basically, the stratigraphic record there reproduced in a fairly good way what is the documented activity. And also, if we consider the beta layer here, it is basically related to what is reported as the main explosive event in the first phase of the eruption. Then I put together our proximal and medial observation with all these data that are collected by Sebastian Watt that went in the field, I think it was about July or August 2008, a few months after the beginning of the eruption. And this just described the distribution of the Tephra deposit that basically have a really huge area of sedimentation. And I here some magnifying the proximal and medial area. And so basically I gave an estimation of the volume for the activity of May 6th and for the activity of May 3rd to 5th. So these two lobes. And these are some of the results. So basically, the Plinian activity, which is the beginning of the phase with a very high, with a production of very high column height and high intensity of the explosion, produce about 0.5 cubic kilometers as a minimum volume, which is more or less half of the overall volume, which is erupted until this is estimated until January 2009. So let's go and see a little bit some grain size. So I focus again on the main explosive eruption. These are the location compared to the isopack map of the points I'm considering. And these are some results. So this is the variation of the median phi. So these red points are my proximal and distal values. The black are the, my proximal and median value. These are the distal. Unfortunately, we have kind of a gap in the sampling of the deposit, but you can see that there is quite a good alignment of these values. And in particular, if you plot in the values of median grain size and sorting, we see that basically they fall fairly consistently in the area for the Tephra fallout. So some general value about the grain size. They show uni and bimodal distribution. The median phi for the proximal area is about minus 2.6 to 1.25, and the sorting range is quite good. Sometimes I could observe in this sample a secondary mode falling in this range of grain sizes that were probably associated with some secondary deposition processes related maybe to some coignin breathing plume during the explosive phase. I also gave a look to the componentry of this sample, and basically there is, in the proximal area, there is a huge amount of lithics that are coming from the disruption of the pre-existing dome, and a second, not so important presence of juvenile, which are divided in obsidian, so a non-vesiculated juvenile glass, and pumices, which is kind of strange to me if we consider this as the overall componentry of the deposit. If you put this in relation to the formation of a 20 kilometers high plume, because usually you need quite a lot of hot material to create a sustained Plinian column, and this look like is not the case. But sorry, oops. So I will come back on that in a few minutes. So this is the calculation of the total grain size distribution of the deposit, basically using this Voronoi tessellation that for each single data point give an area of that is used to create a sort of average, weighted average to estimate this final grain size distribution. So the median phi is 3.8, so a lot, really a lot of fine ash in this case. And what surprised me here is that when I tried to have an estimation of the total grain size using only the proximal deposit, I had a completely different distribution, meaning that if we see how this column are in this tail of the Gaussian of the grain size distribution, they represent basically about 2–3% of the whole deposit. Then this is the thinning plot of the showing how the thickness of the deposit varies with the distance, and I use it to try to give an estimation of the actual volume of the proximal deposit and medial deposit and the distal deposit, considering this point as kind of the point in which the sedimentation process of that characterized the Tephra particles shift from turbulent and transitional to a laminar. So basically this represents that domain of the fine ash. And these are the results. So the proximal and medial represent about 2/3 of the whole volume of this deposit. If I use this value to estimate the actual lithic fraction and juvenile fraction, and considering that the observation on the distal ash described the deposit as composed mainly by glass shard, where the lithic component is about no more than 5%, I have a completely different story from my only proximal observation. So the lithic fraction is basically less than the juvenile fraction. And this is kind of a composition that makes more sense considering the type of activity that was produced. So these are, now we just look at the dispersal, considering how the median grain size and the associated terminal velocity vary with the distance from the vent up to the very end of the deposit. And this is basically a thinning plot considering the area enclosed by each isoline for the median grain size and the terminal velocity. What is visible here is that in this area, the median phi and the terminal velocity vary fairly fast compared to the distal deposit. And basically, once you go over about 130 or 120, depending on what you are considering, basically the terminal velocity stops varying significantly, saying that at this point, probably the diameter is no more a primary factor in the sedimentation of this ash, and something else has to happen to make this particle go down. Also, another thing that is interesting to notice is that the shift from the proximal medial area to the distal here occur fairly at larger distance than what was observed in the thinning plot, considering the thickness of the deposit. And I thought about this, and probably this can be related to some depositional process that involves some aggregation of the particles. In fact, when this particle aggregates, basically they are increasing their diameter, so they basically sediment before or closer to the vent, respect where a single particle would sediment. But when you go and measure the grain size, these aggregates get destroyed, and so basically the effect is that the median phi or the grain size gets reduced. Then some consideration about the pumice texture. So here you see how the density of the pumice fragment that I studied, basically the most represented population has about a density of 700 kilogram per square meter and a vesicularity of about 70%, which is fairly normal for a Plinian eruption. There is a high density tail that is represented by this sample, but basically what we observe is that there is a fairly high vesicle number density, which means that we have a lot of vesicle of small dimension. And here in this plot we have some examples. So the blue are basically the low density pumices are normalized for the average vesicularity measured for this sample. So the pumices are completely almost lacking in crystal. So basically the process of bubble formation is a homogeneous nucleation event. It means that probably the magma that was rising started nucleated bubbles fairly late during the ascent of the batch. So basically, this magma could arrive to a shallow level without solving a significant amount of volatiles and was really in a condition of disequilibrium. If we translate the vesicle number density in decompression rate, it comes out about 10 megapascal per second. So the idea is that something happened during the magma ascent that reduced drastically and violently the pressure, triggering the nucleation of this bubble, so a violent expansion of the gas of the system that produced the Plinian event. So I tried to put together my observation on vesicle with my grain size observation. So here is the particle number density that I calculated starting from the total grain size distribution. So usually this kind of plot are described using a single power law. What happened is that most of the time the real point show a sort of an inflection that maybe are not significative by a point of view of the fragmentation dynamics. But what came out is that if I consider these two power law and I make them cross, I get a breaking slope that is falling fairly close to the median phi, which is itself fairly close to the mode of the vesicle diameter present in the bubble. So the idea is that if the small particles are created, that basically these two interval in grain size can be related to different process of fragmentation. Usually the small particles are more related to bubble burst, have the same dimension of the vesicle and are representing basically the interstitial glass between the bubbles. But here seems that the story is a little bit different, and is one of the possible explanation is that the larger class are more susceptible to collision, abrasion, and a post-fragmentation refragmentation of this particle. That basically, if you just consider if this is the primary fragmentation, it will produce a decrease in the grain size that you observe on the larger class, which is a possible explanation of these two two-segment trend. So, in summary, here just I resume the information. So basically, the Titan eruption developed through a first stage of highly explosive activity, followed by a second stage dominated by the dome extrusion with smaller explosion and minor pyroclastic density currents. The climactic event is estimated to be about 0.2 cubic kilometer and occur on May 6th. The MDV and terminal velocities show that basically there is no diameter of the particle control in the distal sedimentation of the particle, and the discrepancy between what you observe with the thinning trend and the median phi suggests that there is some aggregation process influencing the sedimentation. The fragmentation process is characterized by the sudden release of pressure due to the disruption of the old dome that produced a large lithic fraction of about 40% of the wall deposit. And the particle number density show a multifractal trend that is probably indicating the presence of multiple fragmentation process during the eruption. And that's all. Thank you.
Thank you for a good talk. I might have missed this, but how do you calculate your particle number density?
Oh, well, I didn't go through. Oh, sorry. I didn't go through all the process. The particle number density is determined by standard stereological analysis on backscattered images. So you just, I just took different sample coming from different density class of the population I've observed, and in the end I calculate a weighted average based on the fraction in the density population for each single particle.
Okay, thank you.
Thank you. I have 3 questions for you. One, you show us this photograph about all the layers you discovered after the eruption. How do you could be so sure about that? I mean, you told us at the beginning, yeah, this volcano wasn't have very much record. Am I right? I mean, how do you could be so sure about these deposits were from that eruption, in not another one?
It's fairly obvious if you go in the field. I mean, there was nothing on top of them. On the bottom there was soil. So the only possible origin for that deposit was the Titan eruption. I mean,
okay.
There is really no problem in understanding that if you go in the field.
And how do you calculate the mass of the eruption?
The mass of the eruption basically is elaboration of the volume. So you calculate the volume based on your thinning trend. There are several methods like the exponential method by Pyle, the power law. Now the latest one is the Weibull. And basically, you assume that there is a sort of equation that describes how the thickness of the deposit varies with the distance. Once you have the equation, that equation, you can calculate the integral and you have the volume. After that, you make some assumption on the density of the deposit and you convert the volume in mass.
Okay, thank you.